Well, kia ora koutou e te whānau, ngā mihi nui kia koutou, ko me highway aho, he kaimahi aho matua kai whakahaere, NZARM, New Zealand Association of Resource Management. Nō reira, tēnā koutou katoa. Look, welcome everybody. Thank you very much. Looks like we've got a pretty good crowd given the time of year. End of financial year is looming for many of you. So thank you for participating this time of year. Special welcome to Tom Nation. I've been lucky enough to work with Tom over the last couple of years, so really excited to hear his talk today. I'll let Tom introduce himself. I'll then say, look, he's a very experienced character in this field in GIS with over 15 years experience, and works on a range of environmental projects with himself and his team as well. Just last thing you'll hear from me, just a little bit of admin, and you'll hear me at the end when we do Q&A. Basically how the webinar will work is about 30 minutes over to Tom for a presentation, which is through ARC story maps, which is very GIS of him. And then we'll just go into a Q&A function as well. So if you're wanting to ask questions at the top kind of center of your screen, well, it is on mine, it's just the Q&A button. So probably best to put your questions in there and just as we go, but we'll answer those at the end. Everything is recorded, so including the questions. So that'll be up on the NZARM website in about a week's time from now. So that'll be also emailed out to you if you missed some of this. So there's no problem there. We've got everything recorded. Anyway, big welcome to you, Tom. Thank you very much for giving up your time today, and I'll pass over to you to introduce yourself and take us through the webinar. Cheers.
Brilliant. Thank you, Matt. Thanks for the introduction. Kia ora, everyone. Yes, and thanks for everyone for coming on what is a busy end of the year for most people, I expect. As Matt kind of alluded to, I am going to present today a little bit about sort of catchment mapping, largely around some of the data sets and some of the work that we've been doing recently. And I also want to kind of cover, you know, what LiDAR really is, and that term's kind of been thrown around a little bit lately, and I'll explain a little bit as to why that is and what the kind of things you can kind of do with it and what we've been doing in GIS. So as Matt pointed out, I'm going to present a story map, which is another GIS product, but I'm going to present everything in a story map because it's a nice, clean way to present information. But if you've got any questions, as Matt said, put them in the Q&A box and we'll get to them at the end, I'm sure. So I'll start the presentation. I'll share my screen. So again, as I pointed out earlier, what we really wanted to do here today is it's becoming kind of increasingly apparent that LiDAR is becoming more and more important in New Zealand, and it's becoming more widely available. And so I've been working with this LiDAR data for, as I said, close to sort of 15 years, but more recently it's becoming more and more talked about and as I said, more available. So I wanted to kind of cover that off at the start, talk through some of the common kind of outputs of LiDAR and how they can be used, and then run through what we've been doing in the last couple of years, and particularly in the kind of catchment management space, and then some of the other sort of outputs that we've been able to kind of generate using the sort of LiDAR as the base data set. And I'll go through right at the end some of the new exciting outputs that we're starting to work on, which is sort of combining LiDAR-based data, other GIS information sources, and sort of published science literature. And so that's when it really gets quite powerful in terms of outputs and implementation. So I'll just start rolling through. So as I said, and as Matt pointed out, I work for Collaborations, an applied environmental and water science consultancy. And I've been doing this in the GIS space for about 15 years. So a range of GIS kind of work, but my sort of expertise and my what I'm keen on doing is more around the environmental GIS, which is kind of what we're going to talk about today. And so recently myself and the team have been working on kind of the manipulation of big data, and I'll talk a bit about that, about how big this kind of LiDAR and elevation model information is. But the kind of interesting part of it is being able to manipulate it and create it into practical outputs, and do it in kind of a timely fashion, and be able to customize that. So this presentation, as I said, will run through the publicly available LiDAR datasets and how they can be used to generate useful outputs. I'm going to use Taranaki as an example because we've been working with the Taranaki catchment communities recently, and it's where we've kind of polished a few of these analyses and outputs. But I will go through some of the other kind of parts of the country where we've been working, because I've got slightly different outputs as well. And again, this last sentence here is just talking about how we've come up with a sort of a range of outputs using this data, but there's no doubt many more. And so in the questions and at the end, we'll be more than keen to hear from you about, so other ways we can use the information, or other things you've been seeing on the ground that would be useful to kind of generate from this sort of information. So what is it? So what? So understanding the base information. So in recent years, LINS have published a range of LiDAR-derived data sets. And now you can see in this image below, and this is courtesy of LINS, that, comparing 2020 to 24 in terms of how much coverage we have with this powerful data and really high resolution information. So, and this has come through, some of the funding allocated via the Provincial Growth Fund. But all of a sudden, it feels like, look, 80% of the country will be covered in this information really rapidly. And I think that's why we've been seeing anyway in recent years the term, LiDAR or associated outputs thrown around a lot more. And so I wanted to kind of recognize that and kind of highlight that this is kind of a reason why this is becoming more of a buzzword type thing, and why we're seeing more and more kind of analysis coming out, using this data. Why it's important is a number of reasons why it's important and useful. I mean, it's really high resolution. It's region-wide in many areas of the country now. It's readily available. We can access it now. It's already been paid for. It's available at a time where there are national regulations to consider, which put requirements on farmers or councils to achieve certain things. And it's also come at a time where there's other sort of funding available for other kind of environmental projects and programs. So it's sort of a perfect storm or perfect combination of available information and funding out there to kind of do stuff. What do we do? What is it? So that's kind of, I think, the feeling I get anyway of why this is becoming such a hot topic. So we know LiDAR is now available for much of the country, and you can see that it's potentially, very useful, but what is it exactly? And look, I apologize for people that know what this is, but I think it's important just to run through, more my understanding of it anyway. And it'll help actually explain the rest of my presentation, really, some of the outputs and stuff. So LiDAR, light detection and ranging, is really a technology using lasers mounted to an aircraft or nowadays a drone to get sort of a 3D picture of the land. So here's an image courtesy of LINS. And it's generally that the raw output is sort of a point cloud of highly accurate 3D measurements. But the point cloud itself is very useful, but it's kind of outputs, and we'll go through that in a minute, that are particularly more, are more sort of readily accessible and usable for some of the work that I'm talking about. But just important to know that this is where kind of LiDAR, and this is what LiDAR is and where it starts. And in New Zealand, as I mentioned earlier, we've sort of had this provincial growth fund that has really injected some money and some kind of opportunity to capture a lot more of the country. And going back to that earlier image about from 2020 to 2024, how much more, up to 80% is now covered in this really high resolution, elevation information. So it is available, and you can download it in many different formats. And I was just going to show, if you went right to the source into the raw information, you start getting into this sort of open topography website. So you can see here, and I don't know, out of interest for some people, this might be interesting, how much, in the open topography world, how much of this available data is available worldwide. You see the States has got a lot of information. And if you come down to New Zealand, you'll see, obviously, this is the kind of coverage to date. And if I was to click on, say, Taranaki as an example, we can start diving in and accessing some of the metadata, and we can start coming even further to where you can start downloading this. So here, you can choose, and I'll go through this a little bit, but we can start choosing, okay, I want the ground, and that's what I'll go through soon about elevation models. Or we can start ticking everything and maybe getting a surface model, just pulling out water or vegetation. So the raw LiDAR information is really powerful by itself if you start looking at, the ground returns or the classification. And so we can come through and we can download various formats and various things. Now, this is through the Open Topography website. I just wanted to run you through that to show that this is available to anyone to look at and download. If I go back to the presentation, you'll see this little video here. If I play this, this is the vegetation returns for a little tile in Taranaki. So the colors represent the different elevation, and this is, I'll just play that again, but this is the raw kind of LAS or LiDAR data that comes out of that Open Topography website, just specifically looking at vegetation. So as you can see, it's quite powerful. And if we looked at, say, water bodies, or we looked at the ground, that's where, a lot of the work that I'm going to display comes from. But that's just to give you a little bit of context about LiDAR and its kind of source, it's where it originates and how much of our country is sort of covered by it now. Now, a couple of things, a couple of products or outputs from the LiDAR that are quite common and that we collaborations have been using for a lot of this work are digital elevation models, or DEMs, and DSMs, so digital surface models. And they're available, and they've been generated already, and are available via LINS through the Open Data Service and through this Elevation Aotearoa webpage, which I'll go through a little bit soon. So typically, as I mentioned, apart from using the raw LAS data to show cool visualizations like that or look at specific things, often we're talking about elevation models, which is the ground, and surface models. And the surface model is usually where the laser comes and it's its first return. So it might be the top of a building, or it might be even a power line. It can be that accurate, or it might be the top of some canopy. Now, I'll go through a little bit in a little while why that's really useful and what we've been doing here with some of the work about looking at the difference between elevation and the surface, and some of the products we can kind of create, the analysis we can do with that. So here's just an example here of Taranaki, a nice hill shaded elevation model versus the image behind it. So quite a cool product by itself, really. But the Elevation Aotearoa web page here, which I've already loaded up, this is where, and it looks a bit like that Open Topography website, this is where you can come through and see what LiDAR has been flown, what's in progress, and what's available now. So a really, really useful tool, and I use it all the time to come through and see what's available. You can see these large areas that were part of the Provincial Growth Fund that have been flown now, and Southland has recently come on board. And we've now got data for all of Southland, which is really, really useful. Some of these other areas have, like Canterbury, have got lots of different data available over different time periods. That becomes important again and really useful when you can start to compare elevation or surface models over different time periods at that high resolution to kind of see what's changed. So that, I hope, is the future, where it's not, we can repeat the process and get a lot of this information more regularly, and we can do even more sort of cool things with it. So this is the place to access it. You can click, and actually through here you can go it takes you straight to the data service, and you can start downloading it in whatever format you want. And so this is where we started for our Taranaki work. We started here, started downloading all the individual little tiles and the DEM and the DSM, and we used that as the base for a lot of the work that we've been doing. But I encourage anyone to come through and have a look at this website. It's got some really useful stuff on how to, case studies, some cool visualizations using LiDAR. And one of the cool things here, this shows, again, when I talk about a surface model and an elevation model, this kind of little slider really illustrates that really well. So you can see the elevation on the ground, which are the ground returns, like we talked about with the open topo website, and on the left, the surface model generated from kind of all the returns, or the first returns. So again, I'll show you how the difference between the two here can be really powerful. But this Elevation Aotearoa website, hosted by Linz, is really, really useful and a great place to start if you want to know more information. Along with the LiDAR information, we've been starting to combine that with other spatial data, and that's where you start getting, far more insights, or a lot more kind of, powerful outputs. So when I talk about other spatial data, I'm sort of alluding to the Linz data service, which I showed you before, parcel information, or things like soil type, SMAP, other, bits and pieces, rainfall. And again, I'll show you a little bit later how we've combined some of those spatial data sets along with the LiDAR as the base, to really start creating some useful outputs and products. And then we've found more recently, and this will be the last thing I'll present in the output section, that when we start combining the spatial data with some of the kind of published science literature, then there's some great literature out there and tools, like what Land and Water Science have produced with Landscape DNA. When we start pulling some of that together with the spatial, it becomes really powerful, and we start being able to, create and look at implementation things and more mitigation focused outputs. So again, that's where this is all sort of naturally moving, and where we've become quite excited recently and have the opportunity to work on some projects where we're implementing this. So that's really great. So it all stems from good, detailed LiDAR information in the background. But yeah. So the geo insights analysis, so that's what we're terming at Collaborations, this sort of work that we've been doing, but I'll skip through this bit. This is just talking about what and where and bits and pieces, and who we've been working with Element Environmental with a lot of this work, as Matt mentioned. But I'm going to run through sort of the analysis that we've gone through, particularly in Taranaki, and this is an example from Taranaki, and where and why we did this work. So to just up front, some of the challenges in the catchment. So sorry, I'll zoom back a little bit. So here we go. We want to know a little bit about, and you can see some stock on this image here, but ephemeral and intermittent flow paths are a kind of a key consideration. So understanding where water flows can be a really useful starting point in catchment management and mitigation design. And flow paths, but also importantly, they're contributing kind of watersheds can be mapped by applying the flow direction and flow accumulation analysis to the LiDAR and the DEMs more specifically that we've shown you before. So that's one useful, and it's the first bit that we started looking at. Another useful bit of analysis is looking at topographical wetness, and this is a relatively common and well-known kind of output or product of some of the elevation work. And it's sort of, understanding where water is likely to accumulate based on topography provides a great starting point to map things like critical source areas and identify where mitigations might be placed, to limit contaminant movement throughout the catchment. Erosion-prone land, that's obviously a hot topic in a lot of parts of the country. And and I'll explain a little bit later, there's many different ways and different models out there to sort of map sediment. And I'll run through a few, but we've been working on one that's based on the RUSLE, the Revised Universal Soil Loss Equation. And what's really powerful now is, as you've seen, a lot of the country has this high resolution elevation modeling carried out. And so we can produce some of this erosion modeling and risk-based erosion modeling at a really high resolution, which is quite powerful, particularly at the kind of closer, farm scale. Once you start adding in other information, other spatial data, you start being able to look at things like contaminant load mapping, annual contaminant loads, for example, through literature, other spatial data sets, and elevation models, and I'll run through that a bit later. Riparian vegetation mapping. Now, this is quite cool, and this is sort of a product out of, and as I alluded to before, the surface model and the elevation model. The difference between the two, you start being able to, map things like riparian vegetation and other things, which has been really useful for us. And useful for us as well in our erosion modeling to get an accurate picture of cover, where we know we've got already existing vegetation or gullies are planted that might not be picked up in the land cover database, for example. So another powerful product generated from the DSM, DEM datasets. So specifically, if we start with flow path and watershed mapping, so this is what we've done for, if I zoom out a bit here. So this is an example catchment in Taranaki, and this is some of the flow paths we've been able to generate from the 1 meter elevation model in the background. This sort of zooms in a little bit and talks about the colors here really related to their upstream contributing watershed. So we've put these break lines in this particular example at sort of 1 to 5 hectares, being the little light blue ones here, these kind of ones here, 5 to 10, 10 to 25, 25 to 50 hectares. But we've found that, of course, that these break lines can be adjusted to whatever they need to be, really. And there are some kind of regional rules that where, maybe 8 hectares is a useful number as opposed to 10 or 5. So we found this quite powerful. It's the sort of the base data set for a lot of the work that we've been carrying out. Not only are we capturing the flow paths, but we're sort of creating the contributing watersheds to those. Now they become important, which we'll show later, because you can start quantifying what's in these or what's underneath these contributing watersheds, and the size of them that are flowing to these kind of pour points or outlets. So again, the light blue polygons here or shaded areas are the contributing watersheds to these light blue kind of flow lines. Turquoise being 5 to 10, and say obviously include the 1 to 5s as well. And here we go. Here's some some of the 10 to 25. So as I mentioned earlier, the categories between the flow lines and corresponding catchments can be modified. And something we'll talk about a little bit later, but what we're trying to work on at the moment as well is when you click on some of these watersheds, at the moment, it gives you an area and its size, but we're trying to incorporate some of the characteristics of the landscape underneath these watersheds as well. So to give some kind of context to, what's in that catchment, how much erosion-prone land is there, what's the length of stream under this size, how much actually riparian vegetation is in there, and how much isn't. So that's where this watershed, contributing watershed analysis becomes quite powerful. And again, this is all derived from those nationally available LINS datasets. Topographical wetness, we've talked about this a little bit earlier. I'll zoom out a bit just to show you the same catchment. We've generated these TWI areas of high, high flow accumulation. And so it's actually this method, the TWI method for modeling critical source areas, is kind of one of the methods endorsed in the, in the intensive winter grazing guidance from MFE. So it's quite a well-known product. It's a relatively complex calculation that you do with an elevation model, but it's really powerful. So here, this isn't the blue shaded areas, are areas of high TWI or wet areas. I've filtered these and classified these over a certain number to give, visually, so we can actually hone in on something useful. But the actual raw output of this is quite detailed and quite complicated. But again, this is useful as a starting point. It might not necessarily be where locations are wet, but based on the topography and based on the flow and contributing flow, it's likely that these sort of areas, might be areas where water will accumulate. So it's a good starting point we've found. And here's an example here on the right from Taranaki, actually, where we've got this flow path that we identified in our mapping. You see, note the shelter belt there on the left. Here's the corresponding low point, and the photo, you can't really see it too well, but here's a corresponding low point in the middle here, sort of ground truthing some of the work we've done. So it's quite a powerful way to at least get a starting point for some of these areas where you might want to exclude stock or put some mitigation. So that's TWI. So that's another one of the products or one of the outputs from the elevation model that we've applied in the Taranaki example. Now, the erosion mapping, which I alluded to earlier, I'll just zoom out a little bit just to show. So we've called it granular. That's our sort of term for the work that we've been doing, which is similar to some other products out there. I think in this case, we've been able to leverage the high resolution of the data, the 1 meter scale. And so it is based on the revised universal soil loss equation. And it sort of takes into characteristics like soil type, soil erodibility, steepness and slope length, and that's from the DEM, the LiDAR. Flow accumulation is as well, land cover type, and the rainfall. And so the land cover type, as I mentioned earlier, you can see here, it's excluding a lot of this vegetation, even the small pockets. That's where the elevation and the surface model difference comes in really handy. We can refine the land cover layer so that we're getting a far more accurate picture of what's what's high risk or what isn't. So in this example, orange and red are the high and highest risk areas in terms of erosion prone land. So here on the left here, this sort of shows another real world example where we've identified some erosion prone land on this bank in Taranaki. And on site, this is kind of what it looks like. So again, really high resolution, really detailed, and really useful at that kind of farm scale. One of the other things we've been working on, as I mentioned, was the contaminant load modeling. So this is another area where we can use a range of spatial information, and including elevation models and things to create some powerful outputs. And we've been working in this space. We didn't actually run through this with Taranaki, or not yet, but we've been doing some work in this space with Greater Wellington, which is really useful. Again, as I alluded to earlier, just combining multiple different data sources to start really honing in on some useful outputs. So here's just some really snazzy graphs that one of my colleagues created, looking at nitrogen and phosphorus and their contribution from different land uses. this sort of went into a report for Greater Wellington. We zoom in, we can see that this is sort of a basic contaminant load or land use layer that we've created for this Taranaki example. But you can see how detailed the vegetation mapping can be. And when you start loading in roofs and roads and land use, and tying in sort of national literature on, leaching and load, it becomes really useful. So down here, I'll just open up this. This is an example from the Wellington region looking at zinc loss, for example. So you can see how detailed the mapping is, and therefore getting a sort of an approximate indication of the loss in terms of zinc per year. So again, just another really useful way to use the spatial data, and another good output. The vegetation and riparian kind of mapping, again, doesn't have to be limited to vegetation and riparian, but in this particular case, that's the most useful kind of output for us. Again, we've been using this to sort of refine our land use layers and our land cover layers. But by itself, it's a useful output, a useful product. And particularly, as I said, looking at riparian, so starting to quantify how much of these, intermittent or ephemeral streams greater than a certain area are actually vegetated or not. And so in Taranaki, we've generated this layer for improving our erosion cover factor, but we've also got it there, and it sort of can tie into what the Taranaki Regional Council at least know already about their riparian planting program. So it's got some uses beyond what we're using it for, and we're going to start to try and use it a little bit more in the future. Again, because this data is so widely available across the country, and Lynn's doing such a great job of providing the surface model and the elevation model. So it's really about managing and being able to process the data at this scale. So, and that is one of the challenges that I haven't really talked about, but you kind of need to have good processing power and good ways of data management to kind of be able to use and manage information at this scale, or at this resolution at sort of a regional scale. And so that has been one of our challenges, but we've been working through how best to do that. So again, some of the outputs that we've been working, so just running through all of that, really outlines the analysis that we've been doing. And so what I'll show you now is just some of the outputs that we've been able to create to date. But there are obviously a lot more that we could be looking at. There are a lot more that people on the call will be keen on or have ideas about. So, more than happy to hear all of those. And the more we can use this information, the better, really. But if I just run through some of the outputs we've been generating, particularly for Taranaki, and I've got a few examples from other parts of the country as well. And to tie it all up, some of the latest work we've been doing, and this happens to be in Southland, where, as I mentioned earlier in the presentation, where we've been tying together, literature, science with the spatial analysis. So we'll get to that in a little bit. So some of the outputs you can see, so what we've done all this work, how do people actually access it? What do they do with it? So interactive catchment planning tools are some of the outputs we've been creating. And so ArcGIS at the moment, and that's the platform we use. And you can see this is all built in a story map, which is another kind of output. But there's a range of online web tools that can be built around the catchment mapping outputs. They can be integrated into existing environments. By that I mean existing sort of ArcGIS environments, and we've found, and I'll show you in a minute, where people like Greater Wellington Regional Council have their own environment, and we've been able to create information and share it with them, and they can host it themselves. So the great thing about this kind of work is that the idea is that people can use it, right? We don't want it to sit alone in a PDF document, or we don't want it to be held onto by us or whoever's got a license. We want to be able to share this and for people to kind of manage and use the information. So this particular dashboard is relatively simple, and this is something that we've created for the Taranaki catchment communities. I'll just show you a little bit. Again, a simple kind of map where we can, click here. It gives you a little bit of information about what we're doing. You can click on a catchment, and it will take you to here. I won't actually, up here in the top right corner, you've got some information about zooming in on farm IDs. Now, I won't zoom into anyone's specific farm, but if I can zoom in the middle here, you'll see all of the mapping is available. And you can see as you zoom in a bit further, we've got some of the TWR, the wetness index, some of the erosion-prone land, which is really, really useful. That's an example of a dashboard that can be available. And sorry, I'll just go back to that. And that's where Paul from the Taranaki catchment communities is using that as a kind of a base tool when he's having discussions and workshops with his with farmers and catchment groups. So that's a really useful way to have everything in one place. We've also looked at some dynamic functionality. So when I say dynamic, I mean it's in the background or on the fly. ArcGIS is doing some calculations, which is relatively new and recent in the ArcGIS world, particularly for being available in a web browser. This kind of functionality has always been available to people using desktop GIS software, but we've been able to sort of integrate some of this functionality into the web maps themselves. So if I play this video through, it's relatively simple. You click on a farm boundary and it sort of does its calculations, it's spinning the wheels, and then you see here it's summarizing, and it's a bit hard to see, but I'll explain that it's summarizing how much erosion-prone land there is on this farm, how much of the TWI area there is, and it's looking at the links of the stream. So the reason for this is just a bit of a demo, but what's important about this, as I discussed earlier, is that if you really wanted to hone in on contributing watersheds, or how much of X do I have on my farm, or some of those other kind of background statistics or calculations, all of that stuff is sort of doable in a browser now, which is really exciting for me, who's been working with GIS for a long time, just to see how people or the public can have greater access to it. One of the other outputs we've helped with in Taranaki is just some static maps, right? So people still like to have a map. They still like to print it out and sit around a table and draw on it, scribble on it. Maybe use it as a base to then, draw some of their mitigations or something for a freshwater farm plan or whatever it might be. So we've been able to generate a map like this for every farm in the TCC, or the Taranaki catchment communities area. And that's sort of run through ArcGIS Desktop Pro. But again, this is quite a common output that we've seen. There's, as I'm showing you, there's some really great interactive online tools that can be produced, but these kind of static maps still have their place. And so Paul and the team at the Taranaki catchment communities are finding these outputs really useful. As I mentioned before, doing a little bit of work with Greater Wellington Regional Council, and so some of the work we've done some of this catchment prioritization mapping. And again, this is using the RUSLE, the granular erosion modeling, to kind of prioritize a catchment in terms of its mean annual loss rate, how much of it compared to an adjacent catchment, for example. Where do we start? What do we do, and where? Now, I'll highlight again that with the erosion modeling that we carry out, it is one part of the erosion sort of life cycle. It's the superficial erosion. It doesn't take into account stream bank erosion or landsliding, which some other models, CDNet, might do. But in this case, we're finding it really useful for its relative kind of or its risk compared to sort of adjacent catchments. So, we appreciate there's other erosion processes happening in a catchment, but it's still a really useful tool to identify, where it's happening, And is it happening here, or is it happening in the adjacent catchment, or where do we start? Like if we're gonna spend 100 grand on doing something, is it in this catchment or in this farm or over here? So, and it's at such a good scale or resolution that we're finding it for implementation, it's been really useful. And so here, for example, with Greater Wellington, this is a story map on the right here, an embedded story map inside a story map. It's a bit of inception here, but we come down to, these maps here, and hopefully they show. But again, this is a public story map that Greater Wellington have put out and through their Plan Change 1, and this is some of that granular erosion modelling and mapping. So again, this is how this can be integrated into another organisation's environment. But again, how it can be consumed. It's not sitting in a static document. It's available for people to view in a browser, and it's being used, which is really cool. And if I come down to this last point, now this is the work in progress, and excuse me, this isn't is sort of in draft form, but some of the mitigation outputs that we've been looking at, tying in, as I said, the science sort of literature and multiple kind of spatial data sets, and using the elevation model as a base. We're working, luckily enough, to be working with Thriving Southland and the Middle Reedy catchment group, specifically in the Winton Stream. And so this is some of the work we've been trying to progress recently. And if I just zoom in here, this is essentially showing what I've shown earlier in terms of, flow paths and contributing watersheds. But what we're doing here is looking at some of these areas of topographical wetness, applying some kind of logic to them, and identifying some possible locations for mitigation. And so if I was to click, this is the upstream watershed to this green dot here. If I was to click on this green dot, we're starting to now look at what, the makeup of the contributing watershed. So looking at how big that contributing watershed is, what's the mean erosion rate in there, what's the mean slope, other bits and pieces in there, looking at the slope, the soil type underneath this particular point, and looking at some of that, tying in some of that national literature to try and look at, what's the optimum sizing if you were to put something. So we're saying a wetland would be ideal, looking at its optimum size, and then saying if you made it this size, these are the kind of median N and P removal that you might see from a device here. Now, so this is a really powerful, really interesting work that we're sort of looking at now. In this particular case, we're saying a wetland, and actually what's cool about this is we know there's a real world example here that was actually created 2 or 3 years ago, I think. So this is it here. This is our identified kind of area of high flow accumulation, TWI. This is where we might want to put a device. And this here is at the actual device, the actual bund that's been put in on the ground there. So what was really cool in terms of our validation is just seeing this kind of work that's being carried out, and having a little bit of information as to like how much that costs and how much does it treat. So we're lucky enough to have that kind of information for this particular site, which is great. You'll see that it is a bund, not a wetland, and that's purely because of our interpretation of the soil type in terms of imperfectly drained or well drained. And so there's a few things. Poorly drained, this is where combining high resolution data with kind of more coarse grained national data sets, where we have some not issues, just inconsistencies there, but still it's a very sort of powerful output and a really great kind of next step for us into moving into this side of things, and all stemming from what is that great LiDAR kind of base data set. So that's all the outputs. Again, just going through just another snazzy kind of part of the story map, just to show you where we've been working. As I mentioned earlier, and Matt mentioned, we've been working with Element, and we've been doing similar things in Auckland in terms of looking at prioritization using that kind of RUSLE or the soil conservation stuff. Taranaki, catchment communities, we've gone through this, and helping with the kind of almost regional scale flow path and TWI and erosion mapping to help with implementation there. Contaminant load modeling, which I went through earlier, that's specifically with Greater Wellington, and the plan change work we've been doing there in that space as well. And then lucky enough to be working with Thriving South and more recently, and looking at the kind of critical source area mitigation planning work. So again, this, as I mentioned earlier, this sort of started, a lot of this work started for us in Taranaki, but it's moving quickly and lots of people are interested in it. And going back to my earlier comment, that's why we think it was why we wanted to present something now, really today, to sort of, to highlight why we think it's important, why we think it's, a buzzword at the moment, why we think people are interested in it, and just wanted to show you what we've been working on anyway. So I don't know what happened there. It's just refreshed, but that was the end of my presentation. I haven't managed to, sorry, my apologies. I haven't managed to see any of the questions yet, but Matt, if you wanted to jump in now, I'm quite happy to finish up. The last bit was just to say, hey, contact us or Element if you want to find out more. So yeah, keen to hear questions. Hopefully that wasn't too technical. And again, just wanted to show the power of the raw data set, the fact that we've got 80% coverage in New Zealand now, and some of the outputs, just some of them, but some of the analysis that we can do. So yeah.
Thank you, Tom. Excellent job, and I can see a whole lot of hands getting clapped. I don't even know how to do that through the reaction. So yeah, obviously really well received. It's great from my point of view as a catchment manager to have been working with you over the last little while and seeing the evolution of a lot of these tools. It's really taken in another step, and for some people there'll be very new stuff, and some people will be very similar. But what we've got now with LiDAR just really is fantastic, and what you've done around bringing those tools so it's usable, for practitioners particularly is amazing. So I think it's a really exciting stage that we're in. So yeah, the future is really bright, I think, for LiDAR and GIS, and the improved data, the tools that you've presented, and just really want to thank you, ka mauti wehe. It was awesome, Tom. So we do have some Q&A. Just a reminder, while we're talking the next little bit, this is all recorded. You can go back over it again if you like. Tom's details will be in there as well if you want to contact him directly. And Tom and the team are very highly skilled people. I would highly recommend working with them or reaching out to them. We do have a few Q&A, Tom. You can open that yourself probably as well. But please just add in any Q&A that you have, any questions you might have for Tom before we shut down. If there's any that we can't get to or don't know the answer to right now, we will do that, and it'll be part of the webinar recording. So don't worry too much if we skip on, but I'll read them out for anyone who's just on their phone, if that's all right, Tom, and then just over to you.
Sure.
Thanks again. So one from Mel, just wondering what sort of computing capacity you might need to use some of this information. Good question.
Yeah, and I think using the information and processing it are a couple of different things. I think using it, a lot of it, as I said, is available in a web page and a browser now. So, and there's some kind of really neat ways to publish the really detailed data so that it's not too overwhelming. But in terms of the processing, yeah, I mean, I'm doing it on a laptop. It's a reasonable grunty laptop, but it's nothing. It's not like I don't need a big modeling machine or anything like that to be able to manage it. It's once you start processing things at a regional scale, it does require a reasonable amount of processing power, so to speak. But if you were to pick a little catchment, download the information, run the tools. It can be done on a fairly basic machine, fairly basic laptop. Yeah, hopefully that answers your question.
Thank you very much. Yeah, that's good. One from Alison. Any insight as to why Otago has low LiDAR coverage?
Yeah,
there's a couple of places around the country too that have gaps.
It's a good question. Horizon's another one. Where there are gaps, and the short answer is no. I don't really know why. The detail. I know that looking at the Provincial Growth Fund, LiDAR collection and where they kind of focused on, Waikato Bay of Plenty, Hawke's Bay, Taranaki, Tasman, Marlborough, Canterbury, West Coast, and then they said much of Otago and Southland. So obviously all of Southland, but I can't really give any detail why the rest of Otago hasn't been captured. I know some of Central, a little bit around Queenstown, some of the coastal stuff, but you're right, I haven't. I can't give any insight, unfortunately. It's just a little bit niggly, isn't it, in some areas?
And showing that map at the start, it's a bit of a shame, isn't it? In many ways, that we can't look at the whole country
That's
in
right.
the same way. So yeah, it is a bit of a shame. And I know there was that funded project, wasn't there, that some regional councils took part of and some didn't. So
that's right.
Yeah, I'm sure it'll catch up. Yeah, thank you. Good question, Elson. Last one that we've got on the list, unless there's anything else that comes through, is just a practical one. Will the resources and website links shown be shared afterwards? So is there anything in there, Tom, that you can't share, or are you happy to share those links?
No, I can share the links. Yeah, absolutely. Some of that is actually public already, the middle section. But if you find it helpful to have the kind of blurb at the start about the LiDAR and some of this, then absolutely I can share that. Yeah, it's all a lot of the information at the start anyway is taken from LINS and other places. So, yep, share that.
Excellent, thank you. And just a reminder, this talk will be available on the NZARM website along with many other webinars that we've had over the years. Just one final comment, I suppose, from many of us in NZARM practitioners and catchment managers, and this is just really exciting. So thanks, Tom. I particularly like your last bit on the Oreti catchment that has been implemented before, and anyone else who is a practitioner like us, this is really powerful. So we've taken something like that right the way through to implementation. So it's a great tool to have conversations with farmers and catchment planners and coordinators. So some amazing things there. Thank you, Tom.
And
is there any
last
just things from you, sorry?
No, thanks, Matt. And I'll just add to that, because my team is wider than just the spatial component, and so that's where it's really exciting for us to be able to bring in the science. We're a science organisation, we're scientists, so being able to use the spatial component and the data sets, but also some of our science knowledge, that's what's exciting in my head. So it's cool to be working in that space.
Awesome. Well, there's no other, sorry, there is one more questions, I think. Oh, there's further questions up the thing. Okay, there we go. I apologise. Thank you for putting that comment in. I've missed all the questions, Tom. We've got 5 more minutes. You happy to hold on?
Sure.
Thank you. I didn't refresh it. So quick question. Can you see those as well? Quick question on RUSLE, designed for estimating surface erosion. Yes, it's one. Using it for areas where there is mass movement as the main issue could be confusing. So is there anything you want to comment on there? I've started halfway up, sorry, because it was just loading.
Oh, from Bridget, sorry, yeah. So using it for areas where mass movement is the main issue could be confusing. And so that is one of the limitations for using that RUSLE. Like, it doesn't take into account some of the mass movement processes. So that is always a challenge when we're dealing with this work and trying to be upfront about what it is and what it isn't. So there are some challenging aspects to it. I think what we've found is the superficial erosion is a good starting point for some of the implementation stuff, which has been really helpful. So
Thank you, Tom. There's a couple of other questions. Probably only got time for a couple more, if that's okay.
Yeah, that's fine. And I'm happy to try and answer them post the webinar too.
Thank you very much. Yeah, we'll put this on the webpage as well as the Q&A.
Cool.
There's a question from Simon, or a couple actually. If you could outline, so Tom, when you say wet areas regarding topographic wetness index, how wet? And what determines the wetness as a limitation to use or not use for management requirements? Or is there expectation that these all need to be CSAs, for example? It would seem that further interpretation is required.
Yeah, and that is a good point. And again, it's just a starting point, isn't it? It's purely based on topography. So the level of wetness is unknown, and in some cases that might not be wet, depending on soil characteristics or other things. So it is a good point. It has been in that MFE guidance about it's like an approved method to kind of look at that exclusion or intensive winter grazing, that kind of thing. But yeah, I appreciate that it's not necessarily the exact, the silver bullet. This is going to be wet or it isn't. So yeah, again, further interpretation in those areas, site-specific investigation into those bits is important. Yep.
Yeah, and just to confirm, it's based on LiDAR, isn't it? It's not. Yep. It doesn't have soil infiltration rates and those sorts of things. So it's
that's right.
You do have to go, and that's why we looked in Taranaki to make sure that it was applicable. Yeah.
That's right. And that goes into my earlier comment about tying it in with these other data sets. That's when it does become quite powerful by ruling out, say, 30% of it because it's not appropriate. So, yeah.
Well, thanks, Tom. Just one more question and we'll let everyone go. One from Heath, if you can see it sort of halfway up as well. But again, we'll come back to these other questions. Could you help automate or simplify where to run a water system on a hilly sheep and beef farm?
Good question. Yeah. So that goes into more of the kind of implementation part of it, doesn't it? And so I guess with the LiDAR, you can identify those sort of ephemeral flow paths, which is naturally where the water wants to go in theory. And so, yeah, I guess depending on the scale of it, you might be able to, to help design a system using some of that as the base. Absolutely, and work out, roughly work out the contributing watershed and maybe how much water might be going down there. So I think you could, and what I've demonstrated today is like, really the base data. And again, sort of possibilities are sort of endless once you've got the start. Yeah, I think combining it with other information, you could start using it for that, at least as a starting point.
Great, thanks, Tom. Yeah, so many exciting applications. I reckon we could have you on at another stage and just do a whole bunch of Q&A. How can we use this?
Yeah, where we've got to in 12 months or something. Yeah.
Look, on behalf of NZARM, look, thanks very much, Tom. It was a pleasure to host you. Thanks for the wealth of information you passed on and trying to get these great tools into people's hands. Appreciate everyone. You've had a lot of people on this call and a lot of people have registered as well. Appreciate everyone turning up in this busy time of year and go well. Thanks again. All the best.
Brilliant. Thanks, everyone.